Okay, 2003. It used to be on the old test thing that you knew that the first one was always an equilibrium problem. This is a very difficult problem. Aniline, a weak base, if you remember about weak bases, is you can't use Arrhenius theory because Arrhenius theory doesn't work for weak bases because Arrhenius theory says that acids make H plus, but bases make OH minus. Well, this is a base, but it doesn't have OH minus in it. The OH minus is coming from the chemical reaction. So it's a weak base. You have to use Bronsted-Lowry theory. And so what is the equilibrium constant expression? First thing I'm going to do is I'm going to cross out this guy because um, aqueous, aqueous, aqueous. And so Kb will be the concentration of C6H5NH3 plus times the concentration of OH minus over the concentration of C6H5NH2. I think this is a aniline, but benzamine is the real name. Okay, so that's it. So that's crazy. That's not the hard part. 2. A sample of aniline is dissolved in water to produce 25 mils of a 0.1 molar solution. The pH of the solution is 8.82. Calculate the equilibrium constant for the reaction. Okay, so this one's crazy in that this is what we have to do. This is what they told you. The pH was 8.82. From there, we have to realize that the pOH is 5.18 because remember pH and pOH add to 14. Therefore, the hydroxide ion concentration is 10 to the negative 5.18 power because remember pOH is the negative log of the hydroxide ion concentration. So if you're solving for the hydroxide ion concentration, the first thing you're going to do is multiply both sides by -1. And then what's the only thing that undoes a log base 10 is an exponential base 10. So you end up with this 10 to the negative pOH power. And when you do that on your calculator, you end up with that this is 6.6 times 10 to the negative 6 molar. Okay, so that's just a start, but we need to know the equilibrium constant. Well, so what we need to do, I'll switch colors. We have aniline, which is a weak base. And we throw it into water, and it's basic not because it has OH minus in it, but because it undergoes a chemical reaction. Now remember, bases are proton receivers, and so C6H5NH, it was 2, now it's 3. And they gave you this equation, but H plus, it picked up an H plus, so it is a positive sign. And then this must be acting as an acid because it's a proton donor, and so you don't have 2 H's, you have 1 H, and so it's OH minus. Well, I'm going to kind of set up an ice chart. You don't really have to do an ice chart. You'll see in the next couple problems you have to. But they said that this was 0.1 molar. I'm going to come up here. The initial concentration of the aniline is 0.1 molar. And this, remember, pure liquids aren't used. This is 0, this is 0. Now, I'm just going to do this. We know that this is 6.6 times 10 to the negative 6. And so this has to be 6.6 times 10 to the negative 6. And this has, and so what plus 6.6 times 10 to the negative 6 would be 6. So these have to be 10 to the negative 6. Because remember, you get the E row by adding 0 and 6.6. And then this has to be negative 6.6 times 10 to the negative 6. Now that you've had kinetics, as this reaction proceeds, this concentration is going down. These are going up. Now, if you do on your calculator 0.1 minus 0.0000066, you'll see that for all intents and purposes, this is 0.1. You can do that when you know the numbers because you will get you'll get something. I have my calculator right here. Let me just go 0.10 minus 6.6, second EE negative 6, and the calculator tells you that it's actually 0.099934. And it's okay if you use 0.000.099934 because you're going to get the same answer either way. So maybe we'll just use this because remember, you're only supposed to do sig figs on the very last step. Well, so now I'm going to extend this page. And again, let me say that again because I'm saying this really fast. But when you're doing an ice chart, this is what I found with ice charts. Let me go purple. Either you know KB is the given, and you're looking for H plus if it's an acid or OH minus if it's a base, or you know H plus or OH minus given if it's acid or base, and we're looking for KB. Sorry, not KP, KB. And so this is one where we know the concentration. And so these aren't X's. You're used to this being negative X, positive X, positive X. These are actually constants. So now when I do this problem, KB, if you look at your answer for A, I don't really want to write it down again, but remember it's this concentration times this over this. So there's the formula. Probably should write it down, but I'm being lazy. KB is going to be 6.6 times 10 to the negative 6, because that's the concentration of this guy. Remember, they're in the numerator, times 6.6 times 10 to the negative 6 over 0.099934. If you do your sig fig rule here, you would get 0.1, but the deal is you're supposed to do sig figs at the very end. And so what happens in this problem is that when I put that in my calculator and I round to 2 sig figs, I get 4.4 times 10 to the negative 10. And so that's the answer for B. C, the solution prepared in part 1 is titrated with 0.1 molar HCl. Calculate the pH when 5 mils of the acid has been added. Okay, this is a brutally tough problem. So here's what you need to know. It's not really, but remember when we did titration, when you did titration, you know, we had those packets, we did strong acid, weak base. So basically, you have C6H5NH2, which is a weak base. And you're titrating it with HCl, which is a strong acid. And what happens is acids are proton donors, and so you end up with C6H5NH3 plus Cl minus. And I like to put the initial stuff on the top. They told you that you had 25 mils of this, and it was 0.1 molar. And here they told you that they want to know the pH when this is 5 milliliters and this is 0.1 molar. And so an interesting thing happens there. One of the things on the AP exam is that you have to be able to calculate the pH at any point in a titration, meaning what would the pH be at 1 milliliter, 2 milliliters, 17 milliliters, 40 milliliters? And so what happens is, now this is an ICF-VM, so ICF-VM. Higgins said you guys said something like vroom. This is, I'm going to give you this in milliliters, but then remember molarity is moles per liter. So when we do this, and so interesting thing, if I take, again, this is a really tough problem, and this is what you're supposed to use anytime you do a titration problem. Okay, so here's the deal. I got 0.0250 liters because I got to go 1, 2, 3 times 0.1 molar. And if you do that, this is 0.0025. I am not going to worry about sig figs till the end. I just keep them all on the chart because the rules for sig figs is you don't do anything with sig figs till the dead last step. All right, now this is going to be 0.005 liters times 0.1 mole per liter. Liter cancels with liter. Sorry, I should do that over here. And so then this ends up being 0.0005. And now I should have another zero here, but I don't care. I don't care. It's an intermediate. There we go. By the way, this is nothing. Um, it is there, but it's not important because um, this, well, we'll just keep them all, but it's not going to end up being important for this problem. I probably shouldn't have crossed that out. Let me just fix that. It's not that big a deal to fix it. Okay, and then this would be plus, sorry, Cl minus, and now I'm going to go back to blue. Okay, so here's the deal. Now, with limiting reactant, 0.0005 is smaller than 0.002, and so this reaction will stop when all of this is gone. And then these two go down, and these two go up. And the one thing about the AP exam, they will always be nice to you. It's always going to be a 1-to-1-to-1 mole ratio. Now this ends up being 0.0025 minus 0.0005 is this ends up being 0.0020. This goes to 0. This is 0.0005 and this is 0.0005. And then this is why I do this up here, 25 plus 5 is 30. These are all 30. Now, molarity is moles per liter. So here I'm going to take 0.0020 divided by 0.003. And if I do that, now I care about sig figs. This has 2, this has 2, this had 2, this had 2, this had 2. I get 0.067 here. I get 0 here. I get 0.017 here, and I have 0.017 here. Everything has 2 sig figs. Now, this is interesting. Okay, so what's going on at this point in the titration is that you have a weak base. You have no acid, no acid. You have the salt of a weak base, and then you have the salt of a strong acid. Okay, now when you have a weak base and the salt of a weak base, you have a buffer system. And the way that you get the pH is that you have to use the Henderson-Hasselbalch equation. I'm going to extend this page. And because this is a base, I'm going to use the base formula. So let me switch colors. Let me go red. So the POH is the pKb plus the log of the conjugate, the base over the conjugate acid. Now I want to talk about this. There's 2 forms of this equation. Okay, now aniline is a weak base. We're going to do this. So bases are all about OH minus. Okay, base is on the bottom, concentration of the base is on the bottom. When it's an acid, acids are all about pH. A is on the bottom, A is on the bottom. Now, this just comes off the chart. I'm going to take the negative log. We figured out, by the way, this is a classic example of if you make a mistake in one part and you use it in the other part. We just figured out up here that the Kb value was 4.4 times 10 to the negative 10. So when I come down to do this Henderson-Hasselbalch equation, I'm going to use, and all P means is to take the negative log. This is 4.4 times 10 to the negative 10 plus the log, and the concentration of the weak base is 0.067. That's coming right off the chart. And the concentration of the salt of the weak base is 0.017. And so what happens is this goes here and this goes here. And so now the POH is, if I do this on the calculator, I get 9.36. And if I do this on the calculator, I get negative 0.60. And so 2 sig figs, I kept um, 2 places after the decimal. Um, this is 2 sig figs, so 2 places after the decimal. And then when I do this, I get 9.36 plus negative 0.60 is 8.76, but that's the POH. And the problem asks for the pH, so the pH is 5.24. Tough problem. You have to do you have to do an ICF VM chart. And then because you have a weak base and the salt of a weak base, and by the way, anytime you have a weak base and a strong acid or a weak base and a strong acid, you always have a buffer system, unless you're on the other side of the equivalence point and all the weak base is gone. And so that's a tough problem. All right, now, what's the pH at the equivalence point? Now, this is a very easy equivalence point problem because again, this is the equation we get. And this, I think this is the hardest part because the problem is this is 0.1 molar and this is 25 mils. And then this is 0.1 molar. And so you don't even have to do the factor label method. What's the equivalent point going to be? 25 mils. If the equivalence means you have the equivalent number of moles of acid and base. So if these are the same, then these have to be the same. And so the equivalence point is 25 mils. So now if I come down here and I do my ICF VM chart, where this is a mole, and this is a mole, and this is a mole, and this is a milliliter, and this is a moles per liter, what happens is this is going to be 0.0025 because this is going to be 0.0025. This is going to be 0. This is going to be 0. These are the same, so they are going to run out at exactly the same time. And again, they're nice to you on the AP exam. It's always 1 to 1 to 1. This is 0. This is 0. This is 0.0025. This is 0.0025. This is not difficult. It's just tedious. Don't confused difficult with tedious. This is 25 plus 25 is this is 50 milliliters all the way across. And then this is 0, this is 0, and then this is going to be 0.0025 divided by 0.0500. And so what we end up with is that this is 0.050 molar. Which makes sense, people. This is probably overkill. If you have 0.1 molar and you double the volume, it goes from 25 to 50. Each of those concentrations are going to cut in half. Okay, now, interesting. This is salt hydrolysis, because what happens is so let me just give you the background just so that you kind of know what's going on. When you have a weak base and you're titrating it with a strong acid, at the equivalence point and only the equivalence point, the acid's going to overpower the base. And this is going to be, at the equivalence point, it's going to be acidic. So weak base, strong acid is acidic. Strong base, weak acid is basic. If they're both strong, the pH is 7, it's neutral, and they never do weak, weak, it's too hard. So what happens is you got to know that the thing that's happening here is that at the equivalence point, there's no acid, there's no base. This is the salt of a strong acid, so this is weak, but this is the salt of a weak base, so this is strong. And the craziest thing about this problem is, and this I honestly think in the entire 2 years, salt hydrolysis is the hardest part of chemistry. I'm going to go to black, C6H5 NH3 plus is an acidic salt. It has to be, because when you have a strong acid and a weak base, at the equivalence point, it's an acid, and that's because one of the things there is acidic. And so what happens is, using Bronsted-Lowry theory, this thing starts interacting with the water. Well, acids are proton donors, and it makes C6H5NH2 back, plus, so this is an acid. Acids are proton donors, and then this becomes H3O plus. And this is what makes it be an acid at the equivalence point. And the interesting thing is, so now we have to set up an ice chart, because the equivalence point with salt hydrolysis, these are hard problems. And so what happens is this, we're going to set up capital I, capital C, capital E, and we know from our ICFVM chart room that this is 0.050 molar. That's why we did it. That's why we did it. And then this is not used because it's a pure liquid, and this is 0, and then this is 0. And then, remember, salt hydrolysis, this is going to go up X, and this is going to go down X, and so this is 0.050 minus X, and then this is positive X, and then this is positive X. Now, if this problem weren't tough enough, if the Kb value is 4.4 times 10 to the negative 10, what's the Ka value? Well, remember, Ka times Kb is equal to Kw. So Ka is going to be Kw over Kb. Well, Kw is always 1 times 10 to the negative 14, exact. That's why pH plus pOH always adds up to 14, divided by 4.4 times 10 to the negative 10. And if you do that, you end up with 2.3 times 10 to the negative 5. Oh, this problem is so tough. And so what happens is you got to use your solver. X times X over 0.050 minus X equals 2.3 times 10 to the negative 5. And if you put that in your solver, X comes out to be 0.0011 because you only get 2 sig figs. And if you look up here, X is defined as the H3O, which is logically equivalent to H plus concentration. And so, so X is this, and it was defined as molarity. But again, it asks for the pH. So the pH is the negative log of the H plus or H3O plus concentration. And so the negative log of 0.0011 is 2.96. Remember, only this has 2 sig figs, and so the numbers in front are only the numbers after the decimal point count as significant. This is a tough problem, guys. Okay, which value is the best? So here's the deal. Remember now, pH is pKa plus the log of the conjugate base over the acid. So the titration now, we don't even want to know that. Actually, this is probably a stupid way to do this. What is the pH at the end point? Let's go back. What's the pH at the equivalence point? The pH at the equivalence point is 2.96. Okay, so going over here, keeping this in mind, pH is equal to pKa. Well, the pH at the equivalent point is 2.96. We're just going to kind of ignore this because at the equivalence point, the conjugate base and the conjugate acid are the same. And so I mean, what happens at the equivalence point? The acid and the base or the half equivalence point, sorry, the half equivalence point. The acid and the base are the same. Anyhow, you want to pick the one that has a pKa value closest to the pH. Which one of these has, I'm writing with the mouse again, is the pKa value of 3, 7, or 10 closest to the pH at the end, at the equivalence point? Obviously, the answer is, remember we always ask which is the most suitable, so then you just answer the question. Erythrocene is the most suitable indicator for the titration. Always answer the question first, and the reason is being the pH at the equivalence point is 2.96. The best indicator has a pKa value closest to the pH at the equivalence point. All right, that was a long one.